Thanks for attending this talk. Today I'm going to talk about Resurrecting Stuxnet in 2024. And we have a lot of things to say, actually. So let's start. I'm Alessandro Magnosi. I'm a managing consultant in BSI, the British Standard Institution. And I'm known online as Kletsvirus. You can reach me on Twitter or GitHub or whatever. I'm not very active FOSS developer, meaning that I just stare my GitHub issues and do nothing about them, but trying to fix that. For today's agenda, I'll start with a preface. There is already what I'm seeing here. Thanks for coming to my talk. There is a strange stuff on the screen. As a preface, I'm going to talk about Stuxnet and the OT kill chain. Then I will start with an introduction where I will define the scope of this talk, and then we will get from there on presenting previous research about deploying kernel rootkits on Windows systems, and then we will talk about NTFS and CDFS, and then how to abuse NTFS and CDFS to load a rootkit on a Windows system. Now, just for a preface, let's define what this talk is about. This talk has 3 layers. The first layer is Stuxnet, as we remember it, and what was the ecosystem it was operating within. So it was 2010. The main target was Windows 7. Now, it's been 15 years from then, so Windows has undergone a lot of changes since then. So we will define what is the ecosystem that Stuxnet would need to challenge nowadays. And in the third layer, I want to talk about emulation, like how to emulate Stuxnet. And we did an OT engagement, and we were requested to compromise an engineering workstation. And we liked that environment. We did some research. Some research was derived from there, and we want to share what we found, partially at least. So what this talk is not about, because this is also pretty important. So this talk is not about re-implementing Stuxnet from scratch, because we are not the NSA, we are not an Israeli research company, and centrifuges, no centrifuges has been damaged as part of this research, so you can be sure about that. So let's talk about the OT kill chain. The OT kill chain, I don't know how many of you are familiar with that. Of course, it's 2 phases. It's very different from an IT cyber kill chain, because the IT cyber kill chain is around doing your homework, doing a lot of OSINT against the target you're trying to get into, find a vulnerability, web vulnerability, or successful phishing engagement, social engineering, or whatever you want to find a foothold in the network. And then when you establish your foothold in the network, the next thing you need to do is establish persistence, elevate your privilege, and move across the network until you find your objective. In an OT kill chain, there is a second phase, which is, of course, the attack, finding PLCs, in the case of Stuxnet, finding the OT network, compromise the OT network, and compromise the special equipment used, like human-machine interfaces or PLCs. Now, Stuxnet was very complex and was taking care of the full OT kill chain, which is something very difficult to replicate. Of course, Stuxnet was developed by, we think, Israel and US in combined effort, and it was very complex, as I said. The main operational mechanism of Stuxnet was flash memory, and it was exploiting a very simple fact. People trust USB, or trusted at least USB software. Now, after 2010, we had a lot of box saying that USBs were insecure. Like we had the USB killer. I don't know how many of you remember that. That was just physical damage on the host machine. But in the case of Stuxnet was utilizing a shortcut parsing vulnerability to automatically execute code when the USB was inserted into a machine. After that, Stuxnet was composed by two main modules. One was a user mode driver, or a DLL, literally, that was doing the heavy lift and was cloning itself across the network and was exploiting a lot of other vulnerabilities to propagate through the network, and then a kernel-mode rootkit that was used mainly for persistence and for just maintaining a stealth access and a long-term access to the system. As I said, as propagation, it was using like a bunch of 0 days, the NET API and other 0 days, and also it was replicating itself across other USB, flash memory, just to solve the air gap problem. Now, let's define a bit, like this name, Stuxnet, seems a bit clickbait, and I have to be honest, it probably is a bit. The original title was driver path hijack, which was an alternative method for Windows log event evasion, which is a bit strange to have transformed it in Resurrecting Stuxnet, but there are some motives. So we did an OT engagement, and we, as part of it, we were tasked as to compromise an engineering workstation in an OT environment, with an OT environment that was pretty segregated from an IT environment that was owned by the same company. Now, in order to get in, we needed to find a vulnerability. There was no real vulnerability on the external interface of the company, so we needed to go and find a vulnerability on Siemens.com. That allowed us to perform a phishing engagement that was successful, and we had to compromise a pipeline hosted by the same company, and this allowed us to compromise a catalog server that was actually used for first installation of engineering workstations. We were very lucky, I have to be honest with you, but we liked this. This was a successful engagement for us. We just managed to compromise an engineering workstation from the update catalog. We took probably at the end of the second week, but it was successful, so we liked it. We took this environment, we tried to replicate it offline, and we did some research on that, on the offline replica. Now, as part of this research, we developed some framework to help us out. One of it is CDFS lib, which exploits a sort of issue with read-only file system. Like every one of you probably learned that ISOs are one of the red teaming vector have been used probably in the past 5-6 years successfully. Now, once mounted, we will see that an ISO once mounted is a CDFS file system, and it's supposed to be read-only. Now, we found an issue that permits us to rewrite the content of this read-only file system. This alone is not really a security vulnerability, but it's instrumental to perform additional attacks. Now, driverjack is another tool we developed to hijack the path of a driver that has been loaded to fool the Windows log event and the ETW event generated by the load driver, by the driver being loaded on the system. Then, and these two will be part of this talk. Then we also developed RPC exec, which is part of another now less important talk, and coupling NG, which is another framework that it's an evolution of the coupling framework by Monogas, but it solves some problems. So it automatically deals with unproxied calls, and it also solved the stigma of having an additional section because it just merges export address tables together. And then, as part of this research, we also found 4 or 5 vulnerable drivers, but they were just instrumental to the talk. So we'll just look at the process more than the vulnerabilities that we found. And this is the final kind of this is the final malware that we developed. So we exploited a step 7 sign installer. We identified, so step 7 is pretty tricky because it's using a sort of secure boot. So when you run the installer, it actually performs a security check to ensure that the components have not been tampered with. But we found a way to, anyway, sideload a DLL inside the installer. We used that to elevate our privileges. Then with RPC exec, we were loading the user mode driver and kernel mode driver. And in this phase, we had a problem that was already pointed out. And this is the step 7, how it was implemented. Now, we had a problem that was already pointed out in 2022 by Inversecos, which is, so Stuxnet was utilizing a sort, what we call as Windows event log bypass. So what it means, Stuxnet was trying to be stealthy, loading its rootkit. So it was not using what we usually use, the service start, service create, etc. So it was bypassing the service manager, and it was directly creating a registry key with the service information and the driver location, and then it was just directly loading the driver using anti-load driver. This is a well-known technique that is also has an entry in the unprotect.it, which is maintained by Thomas Rocha, that delivered the talk, I think, yesterday, here. And we have a problem here because, of course, it's become more and more difficult to load a rootkit on a Windows environment. So usually you would use one of three techniques. So the driver needs to be signed because now the Windows enforce driver signing enforcement. So the drivers, of course, need to be signed. But from 2015, you can't really have it signed by an EV certificate or OV certificate. You need to have it cross-signed by the Windows Developer Portal. So the technique used by Stuxnet was they used a leaked certificate, a leaked EV certificate to sign their own driver, but that technique nowadays will not probably work because of this, unless there is a catch. Of course, there is for compatibility purposes, Microsoft introduced a loophole in this kind of policy. So if you have a code signing certificate that is signed and it's expired or been issued before 2015, and it's cross-signed by a valid HVCI certificate, then you can still use it to sign your own driver. The only thing you need to do is fake the timestamp of the driver, of the signature, sorry. And this can still be abused, by the way. And of course, the other technique to load your own rootkit is to use a vulnerable driver to load your own driver in memory. And this technique is known as bring your own vulnerable driver. Now, usually you would use a combination of technique. Usually you have a virtual arbitrary read-write, a virtual memory arbitrary, like a kernel virtual memory arbitrary read-write. But some vulnerable drivers also have the need of having physical memory access. And another technique is use MSR to load, and we will see, to load and execute unsigned code on a Windows system. And the common vulnerabilities then is arbitrary access to model-specific register, physical memory access, and arbitrary virtual memory read-write, as I was saying before. Now, the unprotected MSR is a technique that has been known since 2018. It was leveraged in MSR-exec by Xerox. And exploit a very simple fact. So some of the model-specific register, and in particular the AIA32 All-Star, is used to contain a pointer to the system call handler kernel side. So what this system call handler does, which is the key system call 64, it's an handler that switches to kernel mode and then execute kernel mode code. Now, if we have arbitrary write on an MSR register, what we can do is replacing this pointer with another pointer to a user-defined handler. The only thing we need to do is literally use the handler to disable maps map, just swap, using swap.js instruction to swap the JS and switch to kernel mode, execute our own code, and then use ROP to just restore maps map and restore the original IA32 All-Star. Now, this was a technique that was completely automated in MSR-exec, although it will work probably not so good nowadays, just because we have Intel KChat, and KChat just disabled ROP altogether. Also, it's not that easy anymore to tamper with the IA32 All-Star. There are additional checks due to HVCI. We will see that anyway. Now we have also an arbitrary physical memory access. This always presents himself in the form, and this is one of the vulnerability we found the most. We had 3 drivers vulnerable to this vulnerability. This is usually used for privilege escalation, just because when you have physical memory access, what you can do is that you can map physical pages into user mode buffers, and the result is that you can literally map pages that are retaining e-process structure code. Now, when you find an e-process in physical memory, what you can do is just find in the token and then swap it with the e-process structure that you have in your own CMD.exe or whatever process you want to elevate privilege to. Now, this is not really that much instrumental for us, but it was a vulnerability that we found a lot. And the other vulnerability that we honestly would like to have in a vulnerable driver is an arbitrary virtual read-write. And this is all completely automated, like the exploitation of this kind of vulnerability is completely automated in tools like KDU or KDMapper, and you can use them to load your own unsigned driver. Now, of course, Microsoft don't like this, doesn't like this at all. So since 2018, they did a lot of effort to actually prevent even the exploitation of vulnerable drivers to do real damage against systems. So In 2018, they started introducing a protection that is called VBS, virtualization-based security. And as part of this VBS framework, a lot of additional vulnerabilities have been developed. One of these is HVCI, but there is also credential guard, device guard, and KDP later on. And then with the implementation of kernel chat, and actually in the last years, even Intel VTRP, redirection protection, they really made things harder to exploit. Now, of course, in 2020, you can see also there is the development of vulnerable driver blocking, which is the blocklist, what we know as the blocklist. So before HVCI, what we used to, you just needed an arbitrary read-write to get rid of the driver signing enforcement. So you just needed a read-write in the kernel. You could just point out, identify through memory scanning the location of the G options variable, which is the one that takes the state of DSC in the system. It's protected by patchguard, but you can modify it for short period of times, because as you know, patchguard doesn't run continuously, but it has discrete scanning. And you would just zero it out, load your own unsigned code, and then restore the G options to its original value to avoid triggering patchguard. Now, with post-HVCI, this thing is really difficult because HVCI, what it does, well, not actually HVCI, but the whole VBS, what it does is that it defines your kernel as untrusted code. Now, the kernel runs in two trust levels. One is VTL 0, which is where your kernel code is running, and the other one is VTL 1, which is where the hypervisor is running. And literally, when you have a vulnerability affecting VTL 0, actually, you can't do much anymore to what is running in VTL 1. And this is done through what is called as second layer access translation, address translation, or APT, or EPT, extended page tables. Now, how it works is pretty much like this, thanks to Satoshi Sanda for the diagrams. So what you have is you have a linear address, and you want to find the physical address that corresponds to that linear address. You need now, before HVCI, you had what was page instructor. You were using the normal page instructor, so you have a 4-layer, you have the PML4, you have the PDT, you have the PD, and you just translate the address in a normal form. Doing kernel to using virtual to physical translation. Now with EPT, now there is a second layer which is completely maintained by the hypervisor. So now, regardless what the arbitrary read-write, you can use it for switching the bit and make a page read-write execute, or just read-write instead of read-execute. Whatever is the thing you do here on this page, the change doesn't reflect on this side of the translation. So you have no more control, you have no longer control of what is readable and what is writable anymore. And this is normal HVCI, which also enforces that a page can either be writable or executable. Now with KDP, they switch this from code to data. So now there are data regions that are protected by KDP and are enforced read-only. Regardless what we can do on this page, we can't do anything on this side of the page, so if something is read-only, I can make it not even read-write. Now, KDP has a design flow, of course, so we're not doomed. We can do something about it, and we can do an attack that is called page remapping attack. So we can literally copy the content over to another page, which resolves to an RW memory page. And copying the content over, we can force the translation on the first layer, which is something we control, over this copy, and this will translate to a read-write copy. This is allowed, but of course there is Intel preventing this. So if Intel VTRP, redirection protection, is enabled, and it's true since Intel 12th generation, this attack is no longer possible. Now, to bypass HVCI in terms of loading unsigned code, We have three different approaches. One is kernel forge, which uses ROP. It uses a dummy thread and a dummy event. It puts the kernel thread in a wait state, and then it uses ROP and an arbitrary read-write to craft directly on the return address to craft an arbitrary kernel call. Now, in another approach is using, and this is very difficult to do, by the way, the second one, is to use the page remapping attack to just copy over the SSDT to another page, which is read-write, and rewrite the pointers of the SDT, so we can have, again, arbitrary calls, arbitrary kernel calls. And the third part, and the third approach is, well, it is to disable code integrity before mapping drivers. So if you gain administrative privileges, you can disable code integrity altogether. Of course, this cannot technically be called a bypass, because we are just disabling the protection. Also, considering this needs a reboot, we would need to achieve some sort of persistence before actually being able to pull it off. However, I would say it's easier than finding a new HVCI bypass, which, on a side note, would mean getting a bounty from Microsoft and see it patched afterwards. So we have something. We have some way to execute code even with HVCI, but we need to get there, because in order to use any of this, we need to load a vulnerable driver. And there is the driver blocklist that is trying to prevent us from doing it. Well, how effective is it? Well, not that much. Has been pointed out by Will Dorman, Yarden Shafir, and a lot of people that this driver blocklist is not really effective. It's updated not really a lot of times, and it doesn't really prevent all the drivers that are marked as vulnerable. And I did a very dirty script, DBL check, and the result was disappointing. And another thing that is problematic about the blocklist is that usually to load a driver, you need to be admin, or at least having the silo driver privilege. And if you are admin, you can disable the blocklist. So it's literally completely ineffective in this case. So there is still the CRL though, the certificate revocation list. This is part of Windows, although Windows say that it's not part of Windows. It's a bit contradicting. So it's in this file here. It's loaded at startup, and whenever you load the driver, of course, it's checked by a system that is called Mincrypt. It's actually Simcrypt. It's open source. Is the Windows version of bcrypt, encrypt. And this is checked, and if the certificate has been revoked, you'll have status image cert revoked. So if you try to load Mimi drive nowadays, and you have the driver block list disabled, you'll probably get this result, because the driver was revoked. Now, let's just address a bit NTFS and CDFS and the relation with the NT-Object Manager, just to understand what we did. So in Windows, there is something that we call NT-Object Manager, which is an NT subsystem that is designed to manage resources on Windows. And it's designed to collaborate literally with and manage resources and give access to resources to other NT subsystems. For example, the process manager, the memory manager, the IO manager, and a lot of other NT subsystems. Now, this is a system that was designed to provide access to resources by name. And why this is important? Well, I mean, of course, this maintains stuff in a hierarchical order. I think you all did at least once seen the NT-Object Manager through WinObject, which is this thing, part of sys_internal suite. And as you can see, there is a sort of directory tree, a hierarchical structure. Now, every of these objects is a directory object and is part of a namespace. And now you have all the things accessed globally with the global namespace, where are accessible by the Win32 ecosystem. And then there are other stuff that, for example, the device that can be accessed by the native, the NT system. Now, if you are a kernel developer, you know that the NT-Object Manager, usually when you develop a driver, you usually register a way to access that driver. A way to access that driver through a symlink to the device object. You register a device under the device namespace, and then you can even register a symlink to the global directory to make it accessible to Win32 application. Now, the concept of symlink is very important because we will abuse it. And the concept of symlink is that it's a name pointing to another name resource, just that. Now, in this concept, we need to understand that symlinks can be temporary or permanent. If they are permanent, usually they are maintained permanently across this system by using an artificial construct, which is an artificial ref count, which is literally something that tells the system something else is pointing to this symlink, so you can't erase it. So literally this. And this happens for a bunch of these symlinks. We will see one that we will abuse later on. Now, NTFS, on the other end, is one of the file systems supported on Windows, as it's implemented in a driver that has the same name, NTFS, and it's also managed by the NT Object Manager. Now, NTFS treats all files as a bunch of attributes, name, security, etc., and stores attributes that are permanent in, that are resident in the MFT file record, which maintains a set of metadata on the system. And instead, it stores on the disk associated with the file non-permanent, non-resident attributes. Now, in NTFS, what we really care is, one thing is we access all files, so all files are accessible by, like all files are a bunch of streams as well that maintains data, like you probably all know about the data stream, which is the main stream on files. And then there is the index allocation, which is the main stream on directories. And every file can be accessed through a triplet, which is file name, stream type, and stream name and stream type. Now, NTFS also has a lot of rich permissions, so it means that every file maintains associated with it an ACL with ACE entries, defining what a user on the system can do or not do on the file. And another important concept that we will abuse as well is reparse points. Now, reparse points are literally we can call it a sort of a side of we can call it similar to like attributes, but they are not really attributes. They just are. They are just properties associated with a file that define how that file needs to be processed. It's very important to see that that reparse points can be of many types. What we usually know probably are the symlink file, the junction file, and the mount point reparse points. These are clear to everyone. There are a lot of other reparse points, and they define how that file directory needs to be interpreted by the file system. It's very important to see that they are a sort of they define a sort of preprocessing. This is important for one reason. So of course, as I said, there are three main points: junction point, mount points, and symbolic links. And the difference in the mount points is a symlink associated with a drive letter. The junction point points to another directory. Usually, it's not impossible to make it point to a file, but that's not the point. And then symbolic links are literally file pointing to other files. They are very different from shortcuts, L and K, that were exploited as part of Stuxnet. They are a completely different thing, because link are regular files. Reparse point are not regular files. Now, CDFS is another of the driver that are managed by the NT Object Manager, and they try to emulate what CD and optical systems are. Now, the threat model in CDFS is very different. So, like anyone can mount an ISO as a file system on the system, and every file on this system is accessible by any user. And the threat model is just assume that the file is read-only, so there is no need to care about who can do what with that file. So there is no need to maintain an ACL, even because there is no way to actually know, because they are optical disks, there is no way to understand what user and in what system will access that file. Now, the CDF driver at the NTFS driver is maintained by the NT Object Manager, so you will have, when a user is trying to request a file on a CDFS as it is on NTFS, the IO manager will get the request and will dispatch it to the correct driver for that specific file system. And this is done by the filter manager, of course. I mean, every driver maintains a mini filter related to its own resources. Every file object has a device driver associated with it, and it can be dispatched in this way. Now, during a CDFS read operation, when the ISO is mapped the first time, what it happens is that the CDFS driver will do a common read to take all the content and map it in memory. So the emulated file system now is ready to be accessed. Now, when we try to read a file, what happens is that is the UDFS file system that is actually driver, that is actually calling what we have as CC copy read. Now, the CC copy read will take this file object, which at this point will have a device object associated. I didn't show it because I forgot, but as a device object that is actually an UDFS, an UDF file object, and it will just give it back to us. Now, there is a problem with this file mapped in memory. We found that this file can be remapped, if we want, to a read-write page. And by remapping this file on a read-write page, we can overwrite the content of this file. Now, here you can see that we have a file on this ISO file. We type it. If we try to write to the file, the access is denied. But if we try to rewrite it in another way, so by using this trick, the remapping trick, we can actually rewrite the content. And that is persistent, that is persistent until the ISO is dismounted. Now, this opens to a lot of attacks, to be honest, but we will not delve into all the attacks you can do by overriding the ISO file. So we try to abuse this in combination with other attacks. So we have 3 attacks that we can use, and we can actually leverage the ISO to perform this attack. One is a direct NTFS symlink. Now, this is very stupid attack. We just need trusted installer privileges. We try to create a reparse point, and this is a reparse point. It's a particular reparse point because we are trying to use a name stream without stream type, so to create a link to our resource that is storing on that is stored on an ISO file. Now, if we do that and we restart the driver, this actually works. And this driver is loaded instead of the original, but we have an image load that is very strange. So it's actually pointing to the resource, to the real driver that we're trying to load. This is something we don't really like. So we use an alternative approach. We try to create a structure in the ISO file to make it look more legit. Now, this is WinIO. It's a common vulnerable driver. So we try again to create another reparse point. This, by the way, this is honestly, if you see it from the disk, this seems like the original driver was deleted. It's not the case. We are just placing a reparse point on top of the file. The driver is still there, and indeed you can see that the file size has not changed at all. The reparse point is just get processed before, so that you think that this is being overwrite. But it's not the case. If we restart this, we have again our driver loaded. The problem is now it seems pretty much legitimate, but there is this driver letter that still stands out. We don't really like it. So we tried, and this is just to prove that the reparse point doesn't erase the file. So if we use futil to delete the reparse point, the driver is still there, the size is the same, everything is restored. So we're not damaging the system in any sort of way. Now we try with NT symlink. Now, a vulnerability that was presented by Jonas Leak that was also used in the Undefender project by APT Tortellini was to exploited this condition. So as you can see, all drivers are loaded by using the system root. Even the one that seemingly don't use it actually use it. Indeed, if you try to catch the driver load and you check where the image of the driver is loaded, you will see that it's actually taking system root to load. Now, what we want to do is analyze this system root. What is system root? System root is an NT object manager link. Now, a symlink. a symlink that redirects to boot device. And what is boot device? Well, boot device is another symlink that points to the hard disk that was used for booting the system. Now, the point of this, the interesting stuff is that system, but this is honestly pretty natural, has the privilege to open this link with delete access. But this link has been marked as permanent, meaning that it has an artificial count, ref count of 1 to make it persistent across the system. Now, there is a trick though. We can, if we open the file with delete access right, we can artificially lower the count by making it temporary. We can call nt-make object temporary. Nt-make temporary object, I think. And if we do, and we perform the attack, we can reload the driver, but we still have this L. So we think, how can we get rid of this L? And we say, well, and we also have this problem, that the WDF-PF sys doesn't have any description, which stands out a bit if you analyze the module loaded within system. And this is how it should appear with this fancy description. So he said, well, we can do something more. Well, we can do a drive swap. Very easy. We can swap the letters. It's as easy as that. It's very silly approach, but it worked just fine. So the original approach was this: mount an ISO, take a file in the ISO, decrypt and overwrite the file with the vulnerable driver that we want to load. Then we change the boot device to CD-ROM. We swap the drive letters. We load the driver. Then we restore the drive letters, restore the boot device, and unmount the ISO. So that would be the. Now, alternatively, we will show a demo just after this. Alternatively, we can also use another approach. In the original research by Undefender, they used a WEFI partition. We can use something similar. We can use directories that are used by the TFS file system to store backup data and metadata. Now, these directories should not really be writable by users, but they are. So if you open these files with restore and backup privilege, and with file open backup for backup intent, you can actually write into this kind of paths. These are not enumerable by the Win32 by the Win32 layer, because they're not supposed to be accessed, and they're just used for metadata. But you can actually access them if you open it with this intent. Now, just a silly demonstration of the attack. So with HVCI, we did no integration whatsoever. This has to be very soon we are going to integrate it with a lot of other framework for direct kernel execution like LP Mapper. But so far we're just demonstrating what happens when we try to load this driver using this approach, driver jack. And so we created the ISO, mapped the content, rewriting everything that is on the ISO. Then we just swap everything, and we have the driver loaded, and the driver loaded is this ELPS GPO, and actually show the correct information. If you open the file location, it will actually point to C. So there is no problem, like everything seems fine. Now the next thing we want to show is that the event in ETW, in the ETW event, how it is in Sysmon. And it's perfectly fine. So it seems like the driver loaded was the correct driver loaded. Now, if you combine this with LP Mapper, you will have immediate kernel execution, because the difficult part of LP Mapper is actually how it's combined with the vulnerable driver. Once you have the vulnerable driver, you can use it. In a no HVCI production, we can just link it with KDU, and I don't know if it's firing. We can just link it with KDU, and the only thing that it's literally the same as before. We'll just load the driver, everything will be there. And yeah, KDU just said the driver was already loaded. The vulnerable driver is already loaded because WinAO is there. And then when we just, if like, I don't know if I put anything else. Yeah, this is pretty much it. So this works fine. Oops. Now, just to address the conclusion, I mean, the full attack chain that we did using the step 7 ISO was mostly like this. So we replicated the RSXE. This is, which is a normal executable executed by the setup. And we cloned it. So we had RSC, RS, and RU. And we cloned it because in the process, in the DLL hijacking that we did against the setup, RU would be rewritten and executed. Now, the child process is not really a problem, just because this setup is already creating several child processes. And in the second phase, what we did was using driver hijack and using the same technique. We didn't have KDU in the ISO. We just rewrite a file in the in the ISO to load KDU and load a full kernel rootkit that then would just install a service which was seemingly like the step 7, install the kernel rootkit and search for the other targets on the system. Now, in terms of portability, it's portable. Of course, if there is no HVCI, then you can integrate with KDU. You can remove all the vulnerable drivers that are shipped with KDU. You can just focus on the important part. And instead, oops, sorry. Instead, if Intel, if HVCI is enabled, but Intel KChat is not supported, you can combine this with kernel forge to have, again, to have kernel-mode code execution. If Intel KChat is enabled, but we are still on the 11th generation of Intel, then you can combine it with Malk to do an SSDT override. And if both of them are supported, you still have a way to execute your code by disabling it and rebooting the system. In terms of detection, well, I mean, of course, there are a lot of things you need to do to perform this kind of attack. You can detect system impersonation, for example. You can detect trusted installer impersonation. You can monitor for changes in the boot device symlink. Yes. Or you can implement, this is pretty solid advice, you can implement what is called hash cross check. Now, this is something that it's not a URL rule or anything, but what you can do dynamically when you are reviewing the code is checking the hash of the driver loaded and check the hash of the driver on that path. So if you do a cross check, you will notice that the hash of the driver loaded, even if it's apparently it's the one, it has surely has a different imp hash than the driver on the disk. This is pretty solid detection to this technique. Monitor for drive letter changes. Of course, I mean, it's honestly was a shock that nothing is actually detecting driver letter changes, probably because it's never been abused so far. Deploy recommended blocklist and potentially WDAC, probably in whitelisting because it's just more effective than the blocklist. And well, keep your hardware up to date because as we've seen, the more your hardware is up to date, the more steps you need to do in order to abuse this kind of kernel level attacks. And yeah, I hope it was informative, at least a bit. And thank you. Thank you.